Hello, today we're going to talk about the surface area and volume of right prisms. Now, in terms of this terminology, right prisms, what do we mean by a right prism? Because not every prism is right. A right prism has an identical shape, top and bottom. We call that bottom the base. So an identical shape for the base and the top that are aligned one directly above the other and has lateral surfaces. Now that means side surfaces. Lateral means right next door to the side. Surfaces that are rectangles that make angles of 90 degrees with the base and the top. So when we're looking at a rectangular prism, it really truly doesn't matter which side you consider the base. If we consider the base the one that it is sitting on, then the top would be aligned directly above it. The sides or the lateral surfaces are rectangles and they would be at 90 degrees between the base and the top, that angle between them and the lateral surface. Now this hexagonal prism just means that it has a top and a bottom that are identical congruent figures. The hexagon here and the hexagon here would be identical dimensions. Now you would have to turn it up on its end to consider this the base in the way that we normally think about it, but the base and the top are identical. These lateral surfaces are made of rectangles that are at 90 degrees to the base and the top. Similarly, a pentagonal prism, even a right triangular prism. This diagram isn't the greatest, but you consider perhaps a pup tent. The base and the top are directly aligned with each other and making 90-degree angles with the lateral surfaces. And you can have any kind of prism as long as you have the shape of the base and the top identical at 90 degrees, one above each other. When we talk about volume, we're talking about the dimension, the 3D dimension inside a shape, what it would take to fill that shape. You can think of how much water could I fill this shape with. And when we talk about the volume of any right prism, then if we want to generalize how would I calculate the volume of any right prism, it is always calculated by taking the area of the base, whatever that base is, so finding the area of the pentagon, finding the area of the hexagon, finding the area of the triangle, whatever your base is, and multiplying it by the height of your prism. Now in this one, if we had talked about a rectangular prism, we would find the area of that rectangular base, multiply by the height. Now we've got this hexagonal prism on its side, so this dimension would be the height. We would talk about the area of the base and the height of the prism. Similarly, the area of the base, the height of the prism, you could consider either of these faces as the base, and the height of the prism would be here. And so we have to think about being able to move these 3D shapes around. But in general, that formula will help you find the area, the volume of any right prism. So if we look at a couple of solid examples here, if we had a cereal box that was 19 by 5 by 25 centimeters and wanted to know what is the volume of the space inside, well, we always start with the volume being the area of the base multiplied by the height. In this case, my base is a rectangle, and so my volume would be the area of the base, which is length times width, multiplied by that height, h. And so the formula for any rectangular prism is just length times width times height, which we've known for a very long time. So this would be our length, this would be our width, and this would be our height. We would calculate that with 19 centimeters multiplied by a 5 centimeters multiplied by the 25 centimeters. And the 19 times 5 times 25 comes to 2,375, and centimeters times centimeters times centimeters gives us a 3D dimension for a unit of centimeters cubed. Similarly, to calculate the volume of our triangular prism, we have got the dimensions of 13 for the base of this triangle, 11 for the height of that triangle, And then our slant height here is 12 and 12, and then the height of the prism is 13. And so if we talk about the general formula, the volume is still going to be the area of the base multiplied by the height. But the problem with this formula is I have a height of my triangle and a height of my prism, and we can't use the same letter H to represent two different dimensions. And if you pull out your EQAO formula sheet, it would be very helpful to have that with us. Our EQAO formula sheet on the back has our three-dimensional shapes: the cylinder, the sphere, the cone, the pyramid, the rectangular prism, and the triangular prism. And specifically down here on the triangular prism, you can see that they've chosen to keep the letter H to represent the dimension of the height of the prism, but they've used a letter L, maybe for length. I'm not sure why they've chosen that letter, but the letter L here is representing the height of their triangular base. And so because of that, they've used the formula half base times height we would normally use. Well, they're using half b times L because L is representing the height of their triangle. So don't let that confuse you. Just a heads up to the fact that we can't use two H's or the single H in the formula to represent two different dimensions. But our area of our base is an area of a triangle, and so our base times our height, and we'll use that letter L just because that's what's going to be on our formula sheet, divided by 2, multiplied by the height of that whole prism. And so the volume on your EQAO formula sheet is B times L divided by 2 multiplied by H. And if we fill in the numbers, the base of our triangle is our 13 centimeters. The L is the height of the triangle, the 11 centimeters, over 2, multiplied by the height of our triangular prism, which is another 13. And so we get 13 times 13, which is 169, times an 11 divided by 2. We get 929.5 centimeters. Now, this one's a centimeter, this one's a centimeter, this one's a centimeter. So again, our units for our volume are centimeters cubed. Now, you may not have previously thought of a cylinder as a prism, but it is in fact a right prism, as long as our circular base and our circular top are aligned directly above each other. So if we turn that on its end, this top would be right above our bottom, and we would have a 90-degree angle between the lateral surface and the base. It is truly a circular-based prism. And if we have a circular-based prism where we know the dimension all the way across, that would be our diameter. And so our radius would be 20 centimeters. And again, our volume equation holds true for a circular-based prism. Our volume is just the area of the base. It's just that this time our base is a circle, multiplied by the height of our prism. And so the area of the base, our volume is going to be that pi r squared multiplied by the height of the prism. And so here is our equation for the volume of any right cylinder. Here is our equation for the volume of any right or any triangular prism, as long as we use the L to represent the height of the triangle. And so our volume is pi, which is 3.14-ish, multiplied by our radius that is squared, and our radius has a value of 20. So 20 squared multiplied by the height of that circular-based prism, which is 65. And again, we have centimeters times centimeters, because it's centimeters times itself, multiplied by another centimeter. And 3.14 times 20 times 20 times 65 comes out to a big whopping 81,681.4 centimeters cubed. And so if we had this in a centimeter or 65 centimeters by 40 centimeters in real life, not in a scale diagram, we could take 81,681 little centimeter boxes and fill up that space inside. And so in general, the volume of any right prism, no matter what the shape is, can be calculated by the area of the base multiplied by the height. So if we talk about surface area is a little bit different and a little bit more difficult because we have to talk about not the amount of space inside, but the amount of surface you would paint on the outside. And so with all of our different prisms, we can unfold them into what is called a net. Now, if we think about a rectangular prism first, we can talk about how many surfaces it has. It has a top and a bottom, which are identical. So two of those rectangles. This truly looks like a cube, but it doesn't matter. It could be a rectangle. The front and the back will be identical, so we'll have two of those rectangles. And then the left hand and the right hand side are identical, so we have double that area as well. And so it truly has six faces or six surfaces, but we do have doubles, two of each of them. And so when we take apart a 3D shape, if we can picture cutting along all of those edges where they are connected, we can unfold that shape into what we call a net. And this net diagram actually isn't the greatest diagram for this 3D shape because although it has a, perhaps if we call that the back face, and this is my base that it's sat upon here, and then this would unfold and be the front face. These two, back and front, would be identical. My base would have to be identical to my top, and in this diagram it looks like that top is bigger and that would not fold together shut. So let's just forget about this piece here and truly make the net more accurate. And so with this net we have our dimensions where we've got our left and our right hand side having the 3 centimeter dimension, and that 3 centimeter and the 5 centimeter, actually I guess if that's the 3 centimeter and the side centimeter, or 5 centimeters, then this isn't the base. This would be my, well, I guess it could be, this is my 3 by my 5, because if this is 4, then this is 4. Yep, you're right, this is the base. And if this one's 4, this one's 4. And if this shape, or this piece was connected, we cut this from this one would have to be 4 as well, which means this one is 4 and this one is 4. And this edge would have been connected to this edge, so this would have been 4 and this would have been 4. And our 5 centimeter, 5 centimeter, 5 centimeter, 5 centimeter, 5 centimeter dimension would be on all of those sides. This 3 centimeters would carry through here as well. And so we can see that when we've got our net, the net is the unfolded surface of the 3D shape. And just remember that we get a lot of duplicates in our nets with those unfolded surfaces. Okay, so down here, when we take a look at trying to generalize the surface area of a prism, if I was just talking about rectangular prisms, then I could say, well, I have 2 tops plus 2 sides plus 2 fronts. But if we want to generalize it, we can't talk about that with all prisms because that won't necessarily be the case. We've got a triangular prism here where if we look at the front and the back, or the base and the top, they are my 2 triangles, but then we only have 3 lateral surfaces, and if we unfold those, we could calculate those rectangles. And certainly a cylinder has 2 circles involved with the surface area that you could paint. And if we were to slice down the side of what could be sort of a label on the can and peel that around, that would make a rectangle. And so we would have a rectangle and 2 circles. And so if we want to generalize that, we can say that the surface area of any prism can be equal to the sum of the area of each of the surfaces. So the sum of the areas of all surfaces. Okay, so let's take a look at actually calculating the surface area on that rectangular prism. That rectangular prism, the 3 by 4 by 5, we have a surface area our surface area could be calculated by taking double the area of a side, so a subscript side, not the English word aside, but, and then 2 of perhaps the base and the top. They're identical rectangles, so 2 times the area of the base, so subscript, oh, I forgot my area, 2 times the area of the base. And then we would need the front and back, so that's the same shape, so 2 times the area of the front. Now, if we know this as the length, and this as the width, and this as the height, we would have 2. Our side would encompass our, let's call this the side, our width and our height. So 2 times the area of the width times the height. That would be the rectangle for our left and right side. And then our base is the bottom. That's identical to the top. So 2 times the area of the length times the width, plus 2 times the area of the front and the back. So that would be the length times the height. And on your EQAO formula sheet, they have actually common factored this. There's a 2 in each of those terms, and so they've common factored that out front, saying if you take the width times the height, add the length times the width, and add the length times the height, and if we needed to distribute that 2 back in, we would get back to where we started. But on your EQAO formula sheet, you can see that they have simplified that with our 2 common factored out front. So that's why that formula is the way it is. And if we put our numbers in here, our width is our 3, our height is our 4, plus the length being a 5 and the width being a 3, plus the length being a 5 again and then a 4. And if we do all of those calculations, we would get double, and this together, our 12 plus our 15 plus our 20 comes to 47. And so we finally get double 47, which would be 94. And in here, we've only ever taken 2 dimensions, centimeter times centimeter, and then add a centimeter times a centimeter, and add a centimeter times a centimeter. So we get a 2-dimensional centimeters squared. And so if you were to paint the surface of that entire rectangular prism, you would be painting 94 little centimeters that are squares for our surface area of that entire cube. So let's tackle our triangular prism. For this triangular prism, our surface area is going to be the area of our rectangles, so the area of all the rectangles, however many there are on this triangular prism. On all triangular prisms, there will be 3 of them, plus the area of the triangles, which is the base, triangular base. But my triangular bases, I have 2 of them, so the area of 2 triangular bases. And so my rectangles here, we've got our dimension here of 2.3 meters. This is a very big rectangular cube or prism. And that edge would have been connected to this one. So this one would have been a 2.3 as well. So this rectangle would have been a 0.7 meters times a 2.3. And this one in here, if that's a 0.7, this would be 0.7 times my 1.4. And then this one here, our 0.7 carries through. That dimension is going to be equal all the way, and we'll have 2.7 times a 0.7. And then I'm going to have 2 of my triangles, and the area of a triangle is base times height divided by 2. And so it doesn't matter whether we think of this as the base and this as the height, or if we turn our page and think as this as the base and this as the height. We're going to have 2 of our triangles, so 2 of my base times height, so that 2.3 times the 1.4, all divided by 2. So these 2's cancel out. And so if we were to do our multiplication and add up all of our rectangles, these 3 rectangle areas come to 4.48 centimeters squared. And this 2.3 times 1.4 for the rectangle, or for the triangular area, both of the triangular areas here, will come to 3.22. And if we add those two amounts together, we get 7.7 centimeters squared for the surface area of that triangular prism. Finally, down on the bottom, our circular-based prism, or our cylinder. If we open up that net, we get 3 different surfaces, 2 circles and 1 rectangular area. And this net has been made by actually slicing down, if you can think about it as slicing the label off of a can, perhaps slicing down here. And so the height, and this is supposed to be a 6, I know it's tiny and hard to see, the height of our cylinder would have been 6, and that would have been the sliced edge with the circle not connected to that sliced edge. And so what they've done is they've actually turned our net on its side. And this sliced edge, if you can envision this being the cut down the side, I know the scale isn't the same, but this cut down the side being turned on its side here. So this is my 6 centimeters and my 6 centimeters. And we can see that our radius here is 2. So we've got that as 2 centimeters and 2 centimeters for the radius of our circle. But what we don't have is this dimension here. But remember, this dimension here must have wrapped all the way around that circle if that rectangle was to wrap all the way around, just like a label wraps all the way around the can. And so the length of the edge of my rectangle is going to be the very same as the circumference of my circle. And so let's just write ourselves a little note. And so the length, or you can call it the width, but the length of the rectangle is the same as the circumference of the circle. And we remember that the circumference equation is 2 pi r, or pi d, either one, if you know the diameter or the radius. So if we make a general formula for our surface area of any cylinder can be made with 2 of the areas of the circles, or the area of the base, and then add to it the area of what they call the lateral surface, which is a rectangle. And so we've got 2, and our area of the circle is pi r squared. And then the area of the lateral surface is length times width. But remember that length is the same as my circumference right here. This one is the circumference. And so the circumference is 2 pi r. And then the width of our rectangle is going to be given as the height of the cylinder. And so they call this dimension the height. And so 2 pi r times the height. So this width is the height of the cylinder. And then the only numbers we have to fill in here are the radius and the height of the cylinder. So 2 times pi, my radius in this case was 2 centimeters. Oh, this should be a plus. And then 2 times pi times my radius, again, which is 2, times the height of this one, which was 6. And so when we punch that all in the calculator, 2 times pi times another 2 squared, plus 2 times pi times a 2 times a 6. And you would think that if they're common factoring out the values when they do the surface area of a rectangular prism, in this one you could common factor out the 2, common factor out a pi, and common factor out a single radius and create a simplified equation, but they don't choose to do that. On your EQAO formula sheet, where are we for our cylinder here? Our cylinder's at the top. You can see that they keep it as 2 times the area of the circle, and then 2 pi r for the length, which is the circumference of that circle, times the height. And so they leave it there. They don't do the common factoring for that one. So finally, if you put this all through its mathematical process on a calculator, or if you're going to do it longhand, we get 100.5 centimeters squared. Now, please don't do these questions. We're actually not going to do all of these questions in class. What we're going to do is flip our classroom. Now that you've got your instruction for our period, we're going to be doing some problem solving in class tomorrow.